All right, class. So we finished talking about gases, and I just kind of wanted to bring everything together to make sure you're on the same page as me. So here's a summary. The first thing that we talked about barometer, right? And barometer is used to measure the atmospheric pressure. So we use barometer, and what does barometer do? Is used to measure the atmospheric pressure. And I drew it out for you guys, and I showed you how a barometer works. Okay. Now, the equation that you have to know for the barometer is density of mercury times height of the mercury equals density of a liquid times height of the liquid. This was the equation, don't forget that. And then the densities is usually a constant. Density of mercury, we said this number will always be 13.6 grams per ml. And we said that the heights have to always be millimeters. Okay. Now, the second one you have to remember is PV/nRT. Okay. PV/nRT. And we said that PV/nRT is an ideal gas law. And the only thing you really have to care about in terms of PV/nRT, and let me actually put this in unit, you have to really care about units, okay? You really have to care about units. You get the units down, liters, moles, Kelvin, ATM, you're going to be okay. And then we also said that you can have a problem that is straight up PV/nRT, or you could have changing problems, right? So every time you have a gases problem, you're going to write down the PV/nRT. You go gases is PV/nRT. It could be a straight up PV/nRT, or it could be a changing problem. And changing problems, for example, is when you cancel out the variables that are not changing, and then you move everything to one side, and it's P1, for example, V1 will equal P2 and V2. And we did a bunch of practice problems like that. So again, changing problem, when some of these variables, some of the properties are changing, and then you cross out, for example, here, let's say moles and temperature were not changing, you cross this out, and then P1, V1 equal P2, V2. We did a bunch of practice problems with that. So remember that. So PV/nRT, and then the changing problems that you have to cancel out the ones that are not changing, and then come up with those laws. Then the next one was kind of, don't forget this, that average kinetic energy is proportional to temperature. We talked about kinetic energy a lot. The average kinetic energy is proportional to temperature. I need you to remember that. Okay. Now, the next thing that summarizes what we talked about velocity or speed, right? And we talked about velocity and speed because gases are moving around really rapidly. And we said for the velocity of gases would be 3RT over the molecular weight. Right? 3RT over the molecular weight. And we say that because gases are moving around really, really rapidly, so they have a velocity. We can figure out the velocity using root mean square of velocity. Okay, so far so good. All right. So and then we say that it's kind of like we already know what's going on here. What's really, really important to also know the conceptual questions with this. And the conceptual question is basically when the molecular weight goes down, the velocity goes up, right? So if the molecular, I don't know what that happened. When the molecular weight goes down, what happens to the velocity? The velocity is going to go up, right? And that happens because if you're a lighter atom, you can move around faster, and we talked about that. Now, if you also look at this equation, what happens if the temperature goes up? If the temperature goes up, the velocity will also go up, right? If the temperature goes up, the velocity goes up. If the molecular weight goes up, the velocity will come down. The lighter molecule, they're going to run around faster. You increase the temperature, the velocity is going to be faster because they're going to get more energy to move around faster. So far, so good. Okay, again, T goes up, velocity goes up. Molecular weight goes up, velocity is going to come down because this is the denominator. All right, now the other thing that we talked about is that you can compare two gases. We said that you can compare two gases, okay? So we can compare two gases and then compare two gases, and then my two sound looks really weird. Let me redraw this. So I can compare two gases, and then how do I do that? That was the rate 1 equals rate 2 equals a molecular weight 2 over molecular weight 1. And again, this is a ratio. If you remember, we said this is a ratio. Don't forget that. We're talking about a ratio here. And if you are comparing the gases, and the gases are in the same room, for example, so they have the same temperature, and then the R is the same, so this component goes away, then you can, by dividing the molecular weight, because that's the only thing that's going to matter for how fast they're going, they're infusing and diffusing, then you, by dividing it and take a square root of it, you can get a ratio. Again, if the two gases are in the same room, so the R and T can go away because you're in the same room, you have the same temperature, then only molecular weight matters. So when you talk about ratio, this is what you use. And to get a really nice number to see how much the lighter gas is going to be faster, we said that put the heavier guy on top and put the molecular weight of the lighter gas on the bottom. So this is summarize all that we talked about. Now, let's do a practice problem. Here's a practice problem, and this is a classic question for the exam. In one flask, we have equal masses of O2 and N2, and I asked a bunch of questions. I usually put a question like this on the exam. So pause this video and try to do this on your own. Now, here's the key in this question. One flask, they are in the same flask. If you have one flask, what that means is you're going to end up having the same temperature and the same volume. So if you're in the same flask, you have the same temperature and you also have a same volume. Now the other thing to look out for in this problem, it says equal masses. Equal masses does not mean equal moles. You got to be really careful. You can have the same masses does not mean you have equal moles. And masses, we don't care in chemistry. Moles is what we like. That's why we have a whole hashtag for mole ratio, right? Okay, which one has a greater pressure? So I'm going to write down PV and RT because that's what I know. Every time I have gases, I know PV and RT. Now you're in the same flask, when you're in one flask. If you're in one flask, you have the same temperature and you have the same volume. And R is a constant, okay? So now what we are looking at is pressure and moles. Now it says which one has a greater pressure. If pressure goes up, what should happen to the moles? Moles should also go up. Do you agree? Because they are on the opposite side. If this goes up, that means this one has to go up, so they would equal to each other each side. So the one that has more moles is going to have a greater pressure, because on the opposite side of the equation, moles goes up, the pressure is also going to go up. Now it says you have the equal masses. Equal masses does not mean equal moles. Now which one, if I have equal mass of O2 and N2, which one has more moles? Make up numbers for yourself and then figure it out. That's what I usually do. Equal masses, I'm going to say each one has 2 grams. Again, I'm completely making this up, right? It doesn't matter what the number is, because all I'm going to do, I'm just going to make up number for myself. And I'm going to say, okay, so I have 2 grams of O2. I'm going to convert it to moles. 1 mole of O2 is 32 grams. So I get 0.0625. Then I say I have 2 grams of N2, okay? 1 mole of N2 is 28 grams. So again, I get 0.0714 moles. Okay, so moles of O2, moles of N2. Which one has more moles? N2. this one has higher moles. Okay, the one that has higher moles is going to have greater pressure. Is going to have a greater pressure. So what's the answer? The answer would be N2. So far so good. Again, PV and RT, write it down, cross out the ones that are not changing. There's one flask, so what that means is, that means same temperature and volume. Temperature and volume doesn't matter. So now if I look at it, which one has a greater pressure? The one that has more moles. Because on the opposite side, it has to equal to each other. Again, equal masses does not mean equal moles. How do I know if I have equal mass, which one has more moles? Make up numbers, convert it to moles, and then see what happens. Which gas has a greater average kinetic energy? Okay, which one did you say? Now remember, we said, and I said this a few times, that average kinetic energy only depends on what? Only depends on temperature. Only and only depends on temperature. Are these gases in the same flask? Yes. Does that mean they have the same temperature? Yes. Okay, so what's the answer? The answer would be the same. They're in the same thing, so they're going to have the same average kinetic energy because of the same temperature. All right, here's the next one. Which gas has a greater velocity? Now, when we're talking about velocity, you have to care about molecular weight because the lighter the atom is, it moves faster. Now, O2 and 2, which one is lighter? N2 is a lighter atom because it has a lower molecular weight. So the lighter the atom is going to move around faster. So N2 will be the answer. On your practice exam, I have a few questions like this, and we'll do more practice problems too later to make sure that you guys get down, because I can ask you conceptual question for gases. All right, so I'm going to end this chapter by talking about something that I'm not going to have this on the exam probably, but is nice to know things, because now that you're science majors and you are getting educated in sciences, it's good to know things that you hear on the radio all the time. So greenhouse gases. Now that we're talking about gases, let's talk about greenhouse gases. You hear about these green gas houses all the time and how they contribute to global warming. Okay, which is a very hot topic. Okay. Now, what I don't like about it, how that they've made these greenhouse gases to be the evil of all gases. And that's not the case. That is not the case. So let's talk about these gases for a second. The greenhouse gases are carbon dioxide, 76%, methane, which is 13%, N2O, which is 6%, and chlorofluorocarbon, CFC, it's about 5%. Now, here's the thing. They make these gases to be the evil gases because they contribute to global warming. Now, here's what I do want you to know about them. I completely agree they do contribute to global warming, but we also need these gases. Now, these gases, if they did not exist, if you did not have these greenhouse gases, the temperature right now of Earth, it would be minus 18 degrees Celsius. We would freeze if we did not have these gases. What they do, they absorb heat and they keep it. So the average surface temperature for Earth is around 15 degrees Celsius. They absorb the heat, they keep the average surface temperature to be around 15 degrees Celsius. If we didn't have this, it would be minus 18 degrees, and we would freeze. So they're good for us. But the problem is when we have too much of it, then they're absorbing too much heat, and they're keeping the average surface temperature to be higher than 15 degrees Celsius. So we need them, but we don't want to have too much of it. That's when it contributes to global warming. Okay, all right, we're done with gases. The next one is IMF, and I might actually try to do a whiteboard lecture for that one to see how it goes. Okay, I'll see you guys next time.